then you get what you want actually. Okay. So what did we get as a result of this consequence? That if you have some vague notion of length, which is defined on some subcollection, you can extend it, you can use it to define an outer measure, which is defined on whole space.
Sir, why do you say vague notion of length? Why can't we say measure, any measure, vague?
No, it's not measure. Length is not a measure, because this is what that we are going to do today, an example, okay, in which I'm going to show you that, okay, you can't measure it.
But this
So
notion...
you can't even measure it with the outer measure actually, forget about length. Okay? Forget about length. So if this is the case, that means what actually? That means you have to think about doing something else, like, as I said,
outer measures are
restricting the outer measure on some suitable set. So we constructed measures. Next, what would be that suitable collection on which if I restrict outer measure, it becomes a measure? Okay? This is what the next thing that I would like to do, and then I'll have to do some examples. Definition before going on. Something, it's called the Caratheodry theorem. I would like to define something. So, let mu star be a measure, outer measure. Okay, it's an outer measure. Then any subset of X, then A, which is a subset of X, is called mu star measurable if this happens, and that is that mu star of E can be written as mu star of E intersection A plus mu star of E intersection A complement for all E in X. What this definition is telling? So you define an outer measure, okay, just some kind of a notion of measure, not really, measure in the concrete sense, but okay, you have some notion to measure things, everything in what you call 2 star X actually. Now, as I am saying again and again, that we can show that even if you have an outer measure, you can't measure everything. Okay? So in other words, in this collection of subsets of X, you can categorize sets into the 2 categories actually. Those you can measure with the mu star, and those which you can't measure with the mu star actually. Okay? So here I am defining the sets which you can measure with essentially what you call a mu star actually. Yeah. Set is mu star measurable if what? Okay, how to make sense of this basically expression? What does this expression is telling?
The part of E which you contain in A, it can be measured from
So in other words, what we are saying is this actually. That imagine you have lots of collection of subsets of X actually. So all these are E's actually. Intersecting, non-intersecting, could be anything. And you are taking what? You are taking
A.
A. Okay. Which is this. Now, then I would say that for each E, for example, this particular E, I can say that the part of E, A that lies in E, and the part of A that is outside E, if you sum them up, you get the measure of E star. So if, okay,
Intersecting with A also.
intersecting with A also.
A and A complement.
You can be outside.
So if I take this to be A, okay,
And the small part is E intersection A.
this small part is E intersection A.
Remaining the part of E.
So this
E.
part is
The
basically
remaining part of E is E intersection A
A
complement.
complement. And then if you add these two chunks, like this small chunk and this chunk,
You get the
then
measure of E.
you get the measure of E actually. Okay. So in other words, what we are saying that A is a kind of a set, if if it falls on some other subsets, you can reconstruct it actually. Essentially. Okay. This vague notion will be clear actually if we will see that in all these collections there can be sets which are not measurable actually. So you want to make sure that A is a kind of a set, okay, that the part of A that lies in E and the part of
A complement that lies in E.
or maybe the part of E that lies in A and the part of E that lies in A complement, if you add them, you get the measure of E. And this should be true for every E in X actually, not just one E in X. Anyway, so you call such kind of sets as
B star measure.
mu star measure.
Outer measure.
And the sigma algebra that you want is the collection of all mu star measurable sets actually. That's what is the key thing. Okay. So you have an outer measure. See which of the sets you can measure through this outer measure. Collect them at a single place. That becomes a singular, sigma algebra. Restrict that your mu star, which is defined on whole space, onto that given sigma algebra of mu star measurable sets. Then it becomes a measure.
Complete.
Okay. This is what the Caratheodry theorem is actually. Caratheodry theorem. Okay. So the theorem says that if mu star is outer measure, on X, and A is the collection of subsets of X such that A is mu star measure. A is mu star measurable. Okay? A is mu star measurable. Then A is sigma algebra. This is what we would like to prove. And if you restrict mu star onto A, okay, and give it a name which is mu by just dropping a star, okay, that is going to be a map from A into plus infinity. Okay, it's going to be a map from A to 0 to plus infinity is a measure and A is complete. A is what? Complete. And what is the meaning of complete? That it contains all of its null sets. Okay, it contains its all null sets. So this is what the agenda is. So we have an outer measure, and what we want to do, we want to show that A is sigma-algebra, and we want to show that this restricted
outer measure
becomes a measure when you restrict it onto this collection of mu star measurable sets. And then A is not an ordinary kind of a sigma-algebra, but it's also complete. Okay, so let's get into the proof. One thing which is very important, Caratheodry theorem is different from Caratheodry extension theorem. I'm going to write it in the afterwards. Okay, it's just slightly generalized in the term. Okay. These two results that we have just proved are the second one that we are going to prove becomes a part of the Caratheodry extension theorem. Okay. Why we are doing all that? Because that's a way to construct measure, one thing. That's an abstract recipe to construct measure. This method is important. And in particular, as a consequence of this, I want to define something called the Lebesgue measure.
Right.
Okay. For a given E, should I begin with? So before proving it, I would like to have. Okay, so let's have the remark in the proof. So I'm not starting the proof of sigma-algebra. I'm just giving you a general remark. If you want to show that something is mu star measurable, okay, something is mu star measurable, then you have to show this equality. What I'm saying is that one side of equality is trivial actually. For a given E subset of X, if I want to prove this, then one side is obviously, what do you call, trivial.
सर आपने उसको definition लिखा हुआ है उसको prove करें.
किसको?
ये.
नहीं, समझ रहे हैं? Think about it. So, if I want to prove, for example, so I need to show this as sigma-algebra. I need to show this as a sigma algebra.
सही है
So first I need to do what? I need to show empty set is here. I need to show for every a complement is here.
सही है
So if you want to show that a complement is here, you have to show that this equality that is true for a complement as well.
सही है
So in other words, you have to show again and again this equality if you want to prove this guy as sigma algebra.
सही है
So therefore I'm just giving a general comment there. Okay, if you have any subset of x, okay, and you want to compute its, or you want to show this equality, this mu star of E is always less than or equal to mu star of E intersection A plus mu star of E intersection A complement. In other words, this is trivial. Why this would be the case? Because E is contained in the union of this and this actually. Okay? E is contained in the union of this and this. And then if you operate mu star on it, you get the mu star of the union. And since the mu star is what you will call subadditive, so you get this. So this is trivial actually. So in other words, if you want to show equality, it is sufficient to show. So it is sufficient to show mu star of E bigger than or equal to mu star of, call it a mark, mu star of E intersection A plus mu star of E intersection A complement. Okay?
सही है
So this is what you have to focus on. Now I can start the proof. So how should I start the proof? Let's try to show that A is sigma algebra. The first two properties, in other words, why empty set should be mu star measurable? Do I need to prove it? So E star, so E intersection empty is going to be empty. So mu star of empty is 0. And E intersection A complement, which is going to be a whole x actually, is going to be equal to mu star of, is going to be E actually. And hence you get, so in other words, if you put empty set here and x here, then this will become 0 and this will become what? Mu star of E actually. Okay? So this will become mu star of E. So you have the equality. So indeed empty set belongs to it. So if you take A from sigma algebra, why does A complement should also belong to sigma algebra? This is also trivial actually. Yes, I can write a complement and a complement. This is also trivial. Think about it for yourself. So the only interesting thing would be to prove the 3.
different
Okay? To prove the 3. So for proving the 3, the trick is this. I'm going to first show that A is algebra. So what's the difference between algebra and sigma algebra?
so उसमें finite
So there in algebra you have this finite union belongs to. So if you take a finite collection from, A, calligraphic A, okay, then that finite union must also belong to the calligraphic A. Okay? And to show that finite case, it is sufficient to show that it is true for 2 actually. So if I just show this for A and B, in other words, if I take A and B from calligraphic A and show that their union is also in A, then I can run an inductive argument and show the finite things. In other words, what I want to show, first let us show that A is a theorem. Okay? And to do so, it is sufficient to show that if you take two sets from A, then their union is also in A actually. Okay? If two sets are mu star measurable, then their union is also mu star measurable. Okay? This is what that we have to show. How can I show it? So if A and B are from A, so in other words, this equality is true for all subsets of X. Okay? So keeping in view, if I have a mu star of E, then this is same as mu star of E intersection A plus mu star of E intersection A complement. Agreed? Because A is mu star measurable, so this must be true.
B is also measurable.
Now since B star is also mu star measurable, then if I treat this as a set actually, in other words, if I treat this as E, then I can split this into the two parts as well. Think about it. So in other words, I can write this as mu star of E intersection A intersection B, okay, plus mu star of E intersection A intersection B complement. Agree? And I can do the same trick with this guy. So this must be plus mu star of
E
intersection A complement intersection B.
सर आप इंटरसेक्शन को भी मेजरेबल मतलब अज्यूम कर रहे हैं.
I'm not assuming that as measurable. Think about it. What I'm doing.
सही वो
Definition says
हाँ ठीक है
that if A is mu star measurable, then you take any subset of X,
सही in particular
you can split it into you can split its outer measure into two parts. Any E.
so we are
So first took
ठीक
yes. So first I took E,
abstract
and since A is mu star measurable, I can write this. In the next step, I'm taking this as E,
सही
okay, and then doing the same thing. Plus mu star of E intersection A complement intersection B complement. Agree? And we're almost done with the proof. Proof of the fact that A union B is in sigma-algebra. Why this would be the case? Can you connect the dots where we are heading?
इसको यूनियन में लिखेंगे.
So this guy, so think about A union B. So I can split A union B into two parts. A intersection B and something that is in A not in B, and something that is in B then not in A actually. So essentially if you see these three terms are giving you what? Mu star of E intersection A union B actually. Okay? Not exactly, okay, not exactly, but they are bigger than or equal to. So can I say, so in other words, as A union B is A intersection B union A intersection B complement union A complement intersection B. So if I compute mu star of A union B, so it must be less than or equal to the mu star of these vectors. Okay? Is it making sense? So if this is the case, I can write generally that this means that mu star of E is bigger than or equal to mu star of E intersection A union B plus mu star of E intersection A union B complement. So we showed this inequality, you know, as per remark actually. So the other side is true trivial, so you don't need to prove it. So what does this show? This shows that A union B is in sigma-algebra. Okay? Not sigma-algebra, in A actually. And hence that's what makes this calligraphic A algebra. Okay? Next, what I want to show? Next I want to show that A is indeed a sigma-algebra. This is what. So I'm going to use this property of union being in A. Then I'll try to prove that A is a sigma-algebra. So next we want to show that calligraphic A is a sigma-algebra. So it's a sigma-algebra. Okay. In order to show sigma-algebra, I'm going to show that first of all, that if you take a sequence of A's from calligraphic A, then their union is in also A. So in the first step, I'm going to show that, I'll prove that these A's that I'm taking are pairwise disjoint. So first, I'll not show a general statement, but a concrete thing. So first, we claim that if you take A1, A2, A3, which are pairwise disjoint, okay, pairwise disjoint, then their union I equal to 1 to infinity. AI, it also belongs to it. You don't have a restriction when you want to, prove sigma-algebra. Sigma-algebra, you have to just take a sequence and show that their countable union is in calligraphic A. Okay, but here I'm first showing this for the disjoint case, because I'm going to do what that I'll break down the general case
into different
in the terms of disjoint case. So this is what that I'm going to show. So the next thing is to show this. And in order to show this, what you have to show, so what I have to show, that mu star of E is bigger than or equal to mu star of E intersection this guy plus mu star of E intersection A union B complement. Get this guy complement. This is what that I would like to show. Okay? And this is going to show what I want. Okay. Another. To show this, set